AI video generation models have amazed many with their ability to create realistic videos from simple text prompts. The video you're seeing right now are generated by OpenAI's text-to-video model Sora. In this video series, we'll unravel the mysteries behind AI text-to-video models, and we'll find out how does a simple text prompt transform into a vivid moving picture. At a high level, the process begins with collecting a large number of labeled images and videos. The dataset comprises of millions of samples. You might wonder why images are needed for training. The reason is that we have a much larger dataset of labeled images compared to videos. These images help our AI model learn visual semantics more effectively. Next, the data is fed in batches into a machine learning model, and the model learns to associate text descriptions with visual representation through a process called training. Once the model is fully trained, it can take any text prompt you provide and generate a corresponding video. Now let's look at the process of training in more detail. The first step in training is to compress the input data by using an encoder. Compressing the data is necessary because training models directly with videos or images, which is called pixel space, is computationally very expensive. The encoder is part of a separate AI model which is trained on a large dataset of images and videos. Its primary function is to capture all essential details of input data while reducing its size. Working alongside the encoder is decoder, and decoder's job is to reconstruct the original data from compact representation. To train this model, we pass our input data through the encoder, which compresses it. This compressed data is then passed to the decoder, which decompresses it and generates an output. This output is compared to the original input to calculate reconstruction loss. This loss measures how different reconstructed data is from the original data. To improve the model, we use a technique called backpropagation, in which reconstruction loss is used to adjust the encoder and decoder's parameters. This process is repeated iteratively, updating the encoder and decoder's parameters each time. Eventually, the model learns to compress and reconstruct the data more accurately. For this video series, we will take the example of MagVIT as an encoder, which is designed by researchers from Google. To better understand how encoder processes a video, we can split the video into separate frames. Each frame can be further decomposed into pixels. Now, the grid depicts pixels, which is enlarged for illustration, but in reality the pixels are much smaller. The AI text-to-video models are trained on both images and videos. To effectively handle this, we add padding layers before processing the video or image. The number of padding layers should be one less than the temporal dimension of the first filter we apply. For instance, if our first kernel has a temporal dimension of 3, we add 2 padding frames before the image or video. This allows the 3D filter to process images as well as videos. The encoder comprises of series of computations that are applied on the video. One of them is the convolution filter. Now in the corresponding section, we'll look at how a single convolution filter is applied on the video. Here we have the first 3 frames of a video. Next to them is a convolution kernel that is flattened out, which will be applied to these frames. Each pixel value in the video has 3 numerical values: red, green, and blue. The kernel also has separate weights for each color channel. To apply the convolution, we calculate the dot product, where we multiply each pixel value by its corresponding kernel weight and then add them together. For instance, we can look at a specific example. First, we multiply the red value of 4 by kernel weight of 0.58, which gives us 2.32. Then we multiply the green value of 23 by kernel weight of 0.04, which gives us 0.92. Similarly, we multiply the blue value of 201 with 0.06, which gives us 12.06. This process is repeated and all the values are added together. So the result of applying a 3D convolution filter on a part of a video produces only a single number. We've seen how a 3D convolution operation works when the filter is placed at a specific location. Now let's explore how a filter is applied to an entire video. The filter starts at one corner of the video and calculates a single value, as we saw earlier. It then moves across the video in steps called strides. Strides are usually specified by 3 numbers that represent how much the filter needs to move in each dimension after applying convolution. For example, a stride of 1 into 1 into 1 means that filter moves one step in each dimension, similar to a raster scan as shown here. After each step, the same convolution operation is performed. If our sample video has these dimensions, here 17 represents the frames, 128 is the number of pixels across width and height of each frame, and 3 represents the color channel. In MagVit version 2, we first apply 3 into 3 into 3 filter, and the channels of the input, which is basically the 4th dimension of the data, are increased from 3 to 128. It's important to note that whenever 3D convolution filter is applied, its 4th dimension must match the data's 4th dimension. And also the 4th dimension of the filter is usually not mentioned alongside it. After a single 3D convolution filter is applied, the channel of the data reduces to 1. Since we want to increase the channels, we apply 128 filters of dimension 3 into 3 into 3 with 3 channels. Here each filter has different parameters which pick specific feature from the video. So essentially we get this output. Next we'll apply our normalization technique. Normalizing data helps deep networks converge faster, and a common approach is batch normalization. Batch norm performs well when the batch size or the number of training samples processed together is high. In batch norm, normalization happens across the batch. However, for high resolution videos, we may need to reduce the batch size due to memory constraints. And batch normalization might not perform as effectively. To address this issue, researchers from Meta introduced group normalization. Unlike batch norm, group norm normalizes across groups of channels within a single training sample. By default, the group size is set to 32. For instance, if our data has 128 channels, we would have 4 groups, each with 32 channels. All the numbers within a group are normalized together. To normalize, we find the mean and standard deviation of the set of numbers. Then for each number, we subtract the mean and divide by standard deviation to get the normalized values. After normalization, we apply an activation function. The ReLU or rectified linear unit is commonly used activation function, but recent studies have shown that switched activation function works better for deeper models. The activation function introduces non-linearity. Otherwise, applying a series of filters would result in a linear function. The switched activation function is an extension of sigmoid activation function and is applied to each number in the array. After applying group norm and the switched activation function, we use a 3D convolution filter. This time the channel count remains at 128. This means the filter's 4th dimension is 128 and we need 128 filters to maintain the same number of channels. Next, these filters are applied again and skip connections are introduced. Skip connections essentially take the arrays from a previous point and add them to arrays at a later point. This helps deep neural networks avoid vanishing gradient problems. All these steps form a residual block. In fact, these blocks are applied 4 times while keeping our data dimensions the same. Then we apply another 3D convolution filter with stride value of 2 for both the vertical and horizontal dimensions. This will reduce the second and third output dimensions by half. Next, we apply a residual block. However, one thing to note is that convolution filter increase the data channels from 128 to 256. This means the data dimensions won't match if you want to add skip connections. To resolve this, we use a 1D convolution filter. This adjusts the dimensionality of the array at the previous point to match the dimensionality of the data at the later point. After this, a series of operations are applied. Initially, we increase the data's dimension to capture features better, and then we gradually reduce the dimensions. After performing all these operations, we compress our input data from larger dimensions to more compact dimensions. In this video, we looked at the encoder, which is the first step in the training pipeline. In the next part of this series, we will explore how this compact representation is utilized by an AI text-to-video model.